first of all, this is the volume of a cylindrical shell. By cylindrical shell, we mean not, it's everything, hold on. It's all but the top and the bottom. Okay, so like here, this is a cylinder. Now if this was a can, it would have a top and a bottom, right? But this is like no top or no bottom, just the hollow shell. Okay, just the hollow part. Like if you take a piece of paper and roll it up into a circle to swat flies or something. Okay, or to roll marbles down too. Yeah, that sounds fun. Okay, so the volume is the circumference. Okay, so if this is R, the volume is the circumference and then the height. The volume is the circumference times the height times the, this is like, you think of this as the thickness. Okay, so in other words, this part right here, when it translates, that goes to, that you think of that as being, that dr being this right here, dx, dy. Okay, so let's take a look at this. We got two cases again. So let's look at this one first. This is where you're integrating in an X range, okay? And the context here would be where you have a region that is, let's say from A to B, where you have a region that is bounded by two different curves and then a straight line segments between them. So you got this region right here. Or, I mean, or it could be like where you have two curves that intersect there and then they form a region like that, okay? So it could be a situation like that as well. Okay, but anyways, this is being revolved about an axis, okay? So what happens is if we were to take a typical value X between A and B, then this line segment that goes from the lower curve to the upper curve would be rotated about this axis as well. This would be rotated about the axis, and it would give us a cylindrical shell, okay? So that's rotated around to give us a cylindrical shell. And so you're integrating the volume of that cylindrical shell, which is this whole thing, right? Which is where we get the volume there. Okay, and from A to B. Now this is opposed to the method that we did last time, which is where one thing. Okay, let me say one thing before I say that, and that is the solid revolution. You know, of course, you're rotating this whole region about the axis. So this whole thing's being rotated around. You'll have some solid, and every single line segment between A and B is in this region is rotated around. Okay, so you're basically adding, and the integral is like adding everything up. Okay, now this is opposed to if we were to take cross sections that are perpendicular to the axis of rotation, then you would have washers in this case, and we would be integrating in Y. Okay. Okay. Now, if the upper curve is, let's say, y equals f of x, and the lower curve is y equals g of x, then the height here of this line segment, which is the height right here, is going to be the upper curve minus the lower curve. F of x minus g of x is what the height will be. That's supposed to be an h, not an L. That would be your h of x. So that's where the h of x will go in. The radius in this case is always going to be the distance between the axis of rotation and this. In this case, it's just going to be plain old x. Okay. In this case, that's what our radius is. It's going to be the distance between the axis here and this value here. In this case, it's just x. But if you're rotating over here, then it would be this number to minus x. Okay, so that's what r of x would be. So you kind of have to look at the situation to determine what it is. Okay, over here, this one over here is when you have a region bounded by a couple of curves that's being rotated about a horizontal axis, okay? And so you'd have this being rotated this way. And you would integrate from C to D, would be an integral, okay? And you'd have y. And so naturally what you'd want is you'd want x to be some function of y, and this other curve, try to get that in some function of, also another function of y, okay? So in this case, the r of y would be, so r of y, come on, I'm pressing the buttons on my thing. So r of y would be f of y minus g of y. And then you just kind of have to look at your graph, do a good graph, and then look at it really well to figure out what the circumference and the radius are of what you're trying to do. Okay, great. So let's go ahead and go to some exercises. So first start with number 1. Let S be the solid obtained by rotating the region shown in the figure about the y-axis. Okay, so this is going to be rotated about the y-axis. Here's the y-axis. You're rotating this figure about the y-axis. And so if you take a typical line segment in the region, this is the value of x, then that's going to be rotated over to here. Okay, so I'm just kind of trying to do a rough sketch to help you try to understand what's going on here. Of course, the whole region is being rotated about that. So so it's actually going to end up being a solid. And if we were to integrate in the y direction, we would have washers. Okay. So essentially, one other point that I wanted to make is that essentially this is an alternative to doing the washers. So if you go set up the washer integral and it's really hard, then you can try setting this integral up instead. And here, yeah, the washers is going to cause you trouble because if you're doing washers, then you need to solve this for x. And you're actually going to have to figure out what this point is up here. You'll have to figure out how to get this in terms of x equals something and that in terms of x equals something. It's going to be a big mess with this particular problem to do it using washers. Okay. And oh yeah, there is a part in the question that asks explain why the difficulty is the washer method to find the volume of V of S. You can put whatever you want in there. Doesn't matter. Put whatever answer you want. You could say it's hard to see what the right and left. It's hard to solve for the right and left intervals using this equation here. And even if you did solve these, if you did solve these, then the next question is how are you going to integrate it? That could be really hard. Okay, so it probably could be done, but it might be really hard to do. In this case, cylindrical shells is going to be much easier. Okay, so let's go ahead and try to, and we'll go ahead and set up the integral. So you integrate it from 0 to 2. Okay, and this is a typical value x right there. And it's 2 pi times the radius times the height, okay? That's the, and then dx. Okay, that's what it's going to be. Okay, so, but we can figure out what the radius is. The radius is going to be from here to here, from 0 to x, and that's just going to be x. Okay, so that's x. And then the height is just going to be this value here. So this top point minus there, and the top point is 6x times x minus 2 squared. So we get that. Okay, so that's going to be our integral. And we can go ahead and expand that out. So what do we have? If we combine all these together, we have 12 pi x squared, and then x minus 2 squared is going to be x squared minus 4x plus 4. So distribute this in. So 12 pi x to the 4th minus 48 pi x cubed plus 48 pi x squared. So integrating, we get here it's going to be x to the 5th. So that's going to be that. Because when you take the derivative, then the 5 will just cancel. Here, it's going to be x to the 4th. Now, when we take the derivative, you want to get a 48. And so if you had 12, that would work. So 4 times 12 is 48, so that would work there. And then here, it's going to be x cubed. So 16 will work there, because when the 3 comes down, 3 times 16 is, wait a minute. Yeah, 3 times 16 is 48. Okay, and now it's going to be evaluated from 0 to 2. So putting a 2 in, we have 12 pi, times, okay, 2 to the 5th is 32. And here it's 12 pi times 2 to the 4th is 16. And here 2 to the 3rd is 8. And then when you put zeros in, yay, everything's 0. So minus 0. Okay, I previously worked this out with the calculator, and it's 64 pi over 5. Because that's just too hard to do by hand. Maybe I can show you the, no, I won't do that. Okay, so 64 pi. Now, oh, another thing. Oh. There's a couple other parts of the problem that I forgot about. So let me dispose of those first. This right here is the circumference. Okay. Or this. That's 2 pi x. And this part right here is the height. Also, there's other part that's asking you about the cylindrical shell. So let me just show you it right here. So here we have, along the positive x, here we have the curve. It goes up like that. You can kind of see that. You can kind of see that rotating on. The curve goes up and then down. That's what we had. And in the blue part and the blue cylinder in the middle, that's a typical cylindrical shell. Okay, that's just one of many. They've only highlighted one for you. They could have done a different one. You know, every point where they make contact with this top here is going to give you. So, like if they did using this point here, you would have a wider but shorter cylindrical shell. Okay, so that's the idea there. Okay, so that's the typical one. They have these other ones, which are. This is maybe would happen if you did it using the washer method. Okay, this is what you get for using the washers. And then these other ones are rotating around the wrong axis. Okay, so it's this first one right here. Okay, great. Let's go to the next exercise. Number 2. Use the method of cylindrical shells to find the volume generated by rotating the region bounded by the graph. So the given equations about the y-axis. So you're bounded by y equals 9 e to the negative x squared, y equals 0, and x equals 0. And you're rotating it, and x equals 1, and you're rotating it about the y-axis. Okay. So first of all, as usual, let's go ahead and set up try to draw a good graph that emphasizes everything. Now, y equals 9 e to the negative x squared. This is going to be a graph that's going to go down. When x is 0, so this is the y-axis. When x is 0, we're up here at 9. Okay, and then the graph's going to go down, and it's going to x equals 1. So when we're at 1, then we can make a little chart here. So x, and then 9 e to the negative x squared. When x is 0, this is 9. When x is 1, this is 9. You have a 1 here, so it's 9 over e. Okay, so I'm not going to try to figure out where 9 over e is. I'm not going to try to figure out the exact value, but we'll just say it's right there, 9 over e. And we'll just kind of roughly sketch that coming down like this. Okay, so that's y equals 9 e to the negative x squared. That's the first one. Now we got y equals 0. That's going to be this line segment here, or all the way around. X equals 0 will be this. This is the y-axis. And x equals 1 is over here. Okay, good. So now we know that it's this region here. And that's rotating about the y-axis. Okay, so now it's going to be rotated this way, just about this axis here. And so what will happen is we'll get something that looks like this. And if you take a cross section this way, you'll get a disk. But we're taking cross sections this way. So we'll pick out a typical x value. And we'll see what happens as we rotate that around. As we rotate that around, well, I should have done this lower. Okay, so as we rotate that around, then we get a cylindrical shell. Okay. So the integral, and what we want to do is we want to integrate in the x direction. Okay, so we're going to integrate from 0 to 1 right here. And again, it's 2 pi times the radius times the height dx. Okay, now the radius is going to be, since we're rotating about this axis and the line segment's over here, then the radius is this distance here, which is x in this case. So this time it's x. And the height will be this top point right here minus the bottom point, which will be 9e to the negative x squared minus 0. So 9e to the negative x squared. That'll be the height. Okay, minus 0. So sometimes you'll take the top one minus the bottom one. This time the bottom one's just 0, so that works out nice. Okay, so we got that. And let's go ahead and take the integral. Now, if you have e to the negative, if you differentiate this, you would get this, which is right here, times negative 2x, okay? So let's put a negative there to knock that negative out. And there's a 2 right there, so we'll just forget that 2 and just have everything else. That's 9 pi. Forget the x too, because x goes to. So now, okay, so now here, we'll double check. If you differentiate this, you get this. We get the whole thing, which we got 9 and the pi and the e to the negative x are accounted for. There, and there. Plus you'll get a negative 2x coming down. So the negative cancels, and then you have a 2 and an x. So everything is accounted for when we look at it this way. And you're integrating from 0 to 1. So that's going to be negative 9 pi. We put a 1 in, that's going to be e to the negative 1, which is actually 1 over e. And then subtract, which is actually, subtracting energy is positive, and then 9 pi, and you put a 0 in here, you get 1. So it's that. Okay, so this will be the answer right here. Negative 9 pi over e plus 9 pi.
Could you explain one more time what happened to the 2 pi and the x?
The 2 pi right here?
Yeah.
You mean the 2 and the x?
Yeah, what happened to that when we integrated?
Okay, so what I like to do when I integrate, it's a little bit different than what other people do, because basically what I do is I just guess. Okay, so now I know, and I just guess what, and I take, so what I did is I said I start out with e to the negative x squared, okay? And if you take the derivative of e to the negative x squared, you're going to get e to the negative x squared times the derivative of this top part. Okay, the derivative of negative x squared is negative 2x. Okay, so now this x will be, when I take the derivative of this, I'll get this x, and I'll get this too. Okay, and I'll get a negative, but this is supposed to be positive, so what I did was I put that negative there. So that when I take the derivative of this, I take the derivative of that, I'll get exactly this. That's the idea.
Okay.
Okay, so basically, so it's maybe a little bit different way than you've seen of doing integrals. But I think it's more efficient and much more quicker. For me it is, at least. Basically, I just rearrange, basically the idea is just rearrange and fix this so that when I take its derivative, I get exactly that. Okay, and then start with the main part right here. You recognize that if you take the derivative of this, you're going to get an x. And that's the important part right there. And so then you just rearrange all the rest of the constants so that when you take that derivative of the whole thing, you're just going to get the whole thing here.
Okay, thank you.
Sure, no problem. Okay, so let's move on to the next one. Number 3, use the method of cylindrical shells to find the volume V of the solid chamber rotating the region bounded by the curves x equals 4 plus 1 minus 5 squared and x equals 5 about the x-axis. Okay, so here we're rotating about the x-axis. So let's go ahead and, well, so first of all, try to figure out what this region is. Okay, now this is solved for x. So if it was solved for y, let's say if we had like y equals 4 plus x minus 5 squared. Okay, that would be, there's not this, but this would be, you could maybe recognize this as a, and maybe this 4 is in the wrong spot. Maybe it would be better if the 4 was on the tacked on the end like that, and then you might recognize, oh, that's the standard form for the equation of a parabola, right? And this parabola would open up because this is positive, and the vertex would be 5, 4, right? Vertex would be 5, 4. So what you do is you kind of think of in that terms, but it's x here. X and y have been switched, okay? And so this opens to the right. Okay, here it opened up because it's positive. Here, because it's positive, it's going to open to the right because it's x right there. Here, the vertex would be 5, 4. Here, it'd be 4, 5. Okay, so I'm going to come over here and find a vertex of, go over here by 4, up by 5. That's where the vertex is going to be, and it's going to open to the right. You don't have to get like a really good sketch. You just have to get a rough idea. You just have to get a rough sketch. I mean, this is probably way off. It could be way off, but it doesn't matter that much. And the other one would be x equals 5. So, which here's 4. So I'm going to put a 5 over here, even though it's like, it's obviously not to scale, but it is good enough to get a rough idea of what's going on. Okay, so it's this region, and it's rotated about the x-axis. So that means it's, here's the x-axis. It's rotated here, about this axis, okay? Okay, so what's going to happen is this point gets rotated around. It's a circle. Line segments gets rotated around. Basically, you'll see like this mirror image down here, and it can be rotated like that. And then we can also take a typical, let's say we take a typical, make that y, and that would give us a line segment right here. And we take a typical line segment, and that would rotate like this. Okay, so you get like a band here, or cylindrical shell, what they call it. Okay, so now what we need to do though, before we go any further, is we need to figure out what these limits are. Okay, what's this limit here and what's this upper limit? Okay, what are those values? There's going to be a value less than 5 and one that's more than 5, right? So, and the way to find those is where these points intersect, where this intersects with this. Okay, so what you do is to find those points of intersection. Let me see here. I don't have the colors. I'll use red. Okay, so these are the points of intersection. They're going to be in red. And basically, you're going to take that, and you're going to set x equals to 5 and here. And so you have 5 equals, so this x changed to 5. And subtract 4 from both sides, and you get 1. So that means that y minus 5 equals, or plus or minus 1. When you extract square roots. So let's see, y minus 5 equals 1, y minus 5 equals negative 1. Erase that. Okay, so here you get y equals 6, or you get y equals 4. Okay, so that's actually going from 4 to 6. Okay, so now we're ready to set the integral up. And we're going to integrate from 4 to 6. And Remember, it's 2 pi. Now this time it's going to be r of y times h of y dy. Oops. So 4 to 6. Okay, r of y, that is going to be this distance from here to the axis of rotation. In this case, that's just going to be y. Okay, so that becomes y. And then h of y will be this distance here. From here to here. This is a point on the curve, by the way, the point on this red curve, and this is a point on this line here. So this is because the right boundary is x equals 5, and the left boundary is x equals 4 plus y minus 5 squared, then this distance will be the right boundary minus the left boundary. So the right boundary is 5, left boundary is 4 plus y minus 5 squared. Okay, and then of course we have the dy. Okay, so wow, this is messed up. This is really messy. Okay, so 4 to 6, 2 pi y, what is this? 5 minus 4 is 1. And then over here we have, all this is minus. So minus, if you expand this out, you get y squared minus 10y, but that's going to be plus 10y, and then plus 25, but that's going to be minus 25, because that's a 5 here, by the way. Okay, so integral from 4 to 6. By the way, you can't use symmetry and go from 4 to 5 and then from 5 to 6, because it looks, you know, symmetric right here. Of course, if you're calculating the area, it does look symmetric. But when you're rotating about here, you're going to get a lot more volume from this part of from this upper half of the rotation than you're going to get from the lower half, just because it's rotating to a longer distance. So you can't use symmetry at all and go from 4 to 5 and double it. Although many a valiant student has attempted to do that, but no, it doesn't work. Let me see here. Let me go ahead and distribute those in. So this is minus negative. We'll distribute the y, and so negative y cubed plus 10y squared minus 24y. Yeah, because then if we do that, then we can go ahead and integrate that. Okay, so that's going to be, when you integrate that, you get, integrating this piece is negative y to the 4th over 4. This one is plus 10y cubed over 3, and this is going to be 12y squared. And that's evaluated from 4 to 6. Oh, and we have 2 limits. We can't just ignore the bottom limit anymore. Boo. Okay, so this is, plugging in 6, we get negative 6 to the 4th over 4 plus 10 times 6 cubed over 3 minus, that's a 3, minus 12 times 6 squared. Okay, now subtract, put a 4 in and subtract. So that's going to be plus, and you put a 4 in here, it's 4 to the 4th over 4 minus 10 times 4 cubed over 3. And then this will be plus 12 times 4 squared. Okay, I believe that's it. Let me double check. Yeah, that's it. So I simplified it with the calculator and got 40 pi over 3 as the answer. Okay, great. Any questions before I move on? Okay, let's move on to number 4. Use the method of cylindrical shells to find the volume V generated by rotating the region bounded by the curves x equals 8, y squared, y greater than equals 0, and x equals 8, about the axis x equals 2. Okay, so here, again, this piece right here is a parabola that opens to the right. Okay, so let me try to draw right there. Okay, so this is a parabola. It opens to the right. And the vertex is the origin. Okay, so it's going to go through that point there. And it opens up this way. Now, you have this x equals 8 here, so maybe it's a good idea for us to try to figure out what some stuff is, okay? So this is kind of backwards, but 0, 0, that's the origin. When x is 0, y is also 0. Now, if you think, okay, what value of y will give us, what positive value of y will give us an 8 for x, and that's going to be a 1, right? So if I put a 1 in for y, then I get an 8 for x. Okay, so I'm going to go ahead and put that down. So here, if we come out to 8 for y, no, 8 for x, then y is going to be 1. Okay, so it opens up like this. Like that. And x equals 8 is right here. We'll do that in green. That's the line segment x equals 8 right there. And y greater than equal to 0, it gives us the y-axis. And so this is the region right here that we want to rotate. And we're rotating it out. This time we're rotating it about the axis y equals 2. So that means we come up here to 2. And we're rotating it about that axis. Okay, so what we can do is we'll take a typical y value that's in the range of where we have the thing. Here's the line segment that it gives you, and we'll rotate it about this axis. So that means that what's going to happen is if we come up to 3, if this point here at 1 gets rotated around to 3 as far as height. That's going to give you, that point alone just gives you a circle. Right? This bottom part gets rotated all the way up to 4. So you're basically going to get something that looks like this but it's rotated around, okay? So this line segment that we're drawing here gets rotated up to here. And you essentially have something like this. So here's our cylindrical shell. Okay, something like that. I probably should have drawn it more round, but oh well. Okay, so great. Let's go ahead and find the volume. And you're going to go from 0 to 1 because that's where the region is, and as far as in the y component. So 0 to 1 because we're integrating here. So 0 to 1. Okay, so we got 2 pi r of y, h of y, dy. And that's what we're looking at. Okay, now, here for the radius, here's an example where it's not just simply y. If we just put y in, that's going to get it wrong. And of course not x, because everything has to be in terms of y, right? So that wouldn't work either. Okay, so because what you want, again, is you want R of Y has to be this distance. The distance from here to here, from this part of the line to that part, from this line to that line, from there to there. Okay, now we know, so if you take the top value, which is 2, and subtract the bottom value from it, that will give it to you. Okay, so that is 2 minus y. Okay, so the upper value minus the lower value is going to be that distance. Okay, likewise, we want to take, for the h of x, we want to go from the left part of the endpoint, the left endpoint of this line segment to the right endpoint. And that will be our h of x. Okay, and then here again, you take the right endpoint, which is 8, minus the left endpoint. The left endpoint is this parabola. This is the parabola x equals 8 y squared. So the x value is 8 on the right. The x value on the left part of the line segment is 8y squared. So minus 8 y squared, okay? So that one is going to be 8 minus 8y squared dy, okay? Okay, great. So let's go ahead and figure this out. Let's multiply everything out, multiply those with that. So that's 2 times 8 is 16, 2 times that is negative 16y squared, and then the inside one is minus 8y, and the outside one is plus 8y to the 4th. No, 8y, what am I thinking? 8y cubed. I can go ahead and integrate that actually. So I'll leave the 2 pi there. Integrate each of these terms. So that's 16y. This one will be 16y cubed over 3. This one will be minus 4y squared. And this will be plus 2y to the 4th. Just integrating each part. And that goes from 0 to 1. So 16 minus 16 thirds minus 4 plus 2. And then minus 0, because putting 0 gives everything, makes everything 0, which is nice. And everybody's happy about that, I think. And I worked it out again at 52 pi over 3. Okay, so that's the answer to number 4 on how to do it. Okay, so let's look at number 5, the final question. And we don't have much time left. In fact, we're starting to get negative time at this point. Okay, so the integral represents the volume of a solid. Describe the solid. Okay, so what you want to do is you want to look for, look at this model here, 2 pi r of, this is in y, so r of y, h of y. So compare these together, and it looks like the easiest thing is to make the radius, so this is the same as that, okay? So that kind of just checks off. It's because it's cylindrical. I think the easiest thing is to make this our r of y right here, and to make h of y be that one. So probably r of y being y plus 9, and probably if we made h of y equal to 1 over y squared, that's probably the easiest thing. So now, you think, okay, what will give us, we'll make this radius, we'll make the radius y plus 9. And that would be if you revolve it about, the line y equals 9, that will tend to do it, okay? Because because it's going to be, it's not like if we look at this previous problem, for example, then wait, we revolved it about this 2, right? So it's actually this 2, the radius was 2 minus, or what is it? What's going on? The radius is 2 minus y, right? And if this was negative, it would be negative. It would be maybe y minus a negative 2. Okay. So if you're going to a lower one, it would be y minus a negative 2, or it would be y plus 2. Okay, so that's what would give you that. And then the h would be some value, the right minus the left. Okay. So it's going to be one of those 3. And then, let's see, we want to get the 1 over y squared for the other one. So that looks like it's going to be, looks like this could do it. And it looks like that could do it also. The 2 pi, no. You don't need 2 pi. 2 pi is built in. Okay, so, one of these. It could also be something like this, but I suspect it's not. Well, no, it can't be, because you have to have a y in there. Okay, so this goes from 1 to 2. This goes from 1 to 4. Oh, it's got to be this one. This goes from 1 to 4. And so the limits of integration is that one. Yeah, that works. That looks like it works. Okay.